worksheet. And I am bringing the worksheet. I think I have it up on the screen. So I think I have it like in a view to where it's about the same, like mine's maybe just a little bit more like zoomed in. Okay, so let's talk about your answers that you developed from Monday until today. Okay, so I have the very first question. So in a symmetry-allowed reaction, the symmetry allowed Diels-Alder the lower lobes of the p orbital of carbon 1 or 4 of the diene, and which molecular orbital do we work with for the diene? It is the HOMO orbital of the diene, and then it constructively overlaps with which orbital of the dienophile? The LUMO orbital of the dienophile. Exactly. And so the HOMO orbital of the diene with the LUMO orbital of the dienophile. Okay, so then coming to this next question, so in the 6+2 symmetry allowed, is it just like the 4+2 Diels-Alder? And then I had you go through an analysis. So let's go ahead and also, like, together go through this analysis. And so I have you draw the molecular orbital energy diagram of a 6-carbon, like a diene, in air quotes. What is it really? A 6-carbon triene, exactly. Okay, so then if I have 6 carbons and I'm drawing the energy diagram for a 6-carbon system, how many individual p orbitals did you draw? 6, okay? And so 1, 2, 3, 4, 5, and 6. And then how many energy levels are in the energy diagram? 6. And so then that would be 1, 2, 3, 4, 5, 6. And then energy level 3, 2, 3, 4, 5, 6. And then energy level number 4. I'm not going to take time to draw them all out, but this will give us enough so you can compare your answers to mine. So I've been saying that each of these is at an energy level, but we call them by a name. So this first energy level, this molecular orbital has a name. What do we specifically call that molecular orbital? The pi1, exactly. It is the pi1 molecular orbital. And so then what is the second energy drawing that's a little higher in energy? It is pi2. And then the third is pi3. And then the fourth is pi4. And then what would the next one be? pi5. And then the last one, if I drew it, would be pi6, correct? Okay, so now I've given them all names. So now let's go ahead and talk about the orbital overlap. So in pi1, how would you define the orbital overlap across pi1? It is all constructive orbital overlap. And I'm going to just go ahead and do the shading trick. If I were doing the mathematical signs, it would be plus, 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 plus all the way across. We're all constructive overlap. We have all of these waves that are overlapping for constructive overlap. Okay, that's pi1. So then what is different about pi2 in your drawing? Yep, so it has one node and then where? Yep, in the middle, always in a place of symmetry. And so if I shade in, so this would be plus, 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 what needs to be the sign of the top lobes for pi2? Yep, and so then I'm going to shade the bottom. Okay, what is different about pi3? Yep, 2 nodes. And so then it's going to be plus, plus, and then minus, minus, and then plus, plus. Okay, and then what is different about pi4? Instead of 2 nodes, it has 3. So here's what I do when I'm choosing 3, because sometimes it can get a little odd. I'm just predicting this off the top of my head. So I do 1 in the middle, and then I tend to go, okay, I'm going to put my 3 like that. That is me predicting. Okay, what kind of organic chemists are we? Leafing, right? Maybe we've left budding. We're like leafing. We have the first leaves out, so we're leafing organic chemists. Do our predictions always 100% match reality? They don't. So in your Mastering Chemistry homework, it's giving you, here are the exact pictures orbital energy diagrams. They will be very close to what you predict using your mind, but they're not going to be exact. But we're just leasing organic chemists, and so we do our best at predicting at paper. I know there's trees and places of symmetry. This looks like three symmetric areas. Does that make sense? I just want to explain why sometimes the pictures we draw in class might be a little bit different than how they're officially drawn in your textbook. So then I can draw the pi4 like I kind of drew up there, but then if I really wanted to know what does the pi4 molecular orbital of the hexatriene look like, what would I do? Hey Google, what does the pi4 molecular orbital of hexatriene look like? That's what I would do. So I know that mine is a educated guess, and it is close enough that it is not going to matter to any of the chemistry we're drawing if I'm a little bit off on where I think it is. Okay, does that work for everyone? Okay, perfect. Okay, so I'm not going to go through and draw this, but it sounds like you have great ideas about what they look like. Okay, so then pi1, pi2, pi3, pi4, pi5, pi6, not all of them have electrons. Which of these orbitals do have electrons? Yeah, so pi1 has 2. Pi2, how many electrons? And pi3 has? Oh, okay, so then what do I refer to these molecular orbitals as? They are my bonding molecular orbitals, and then there is often in such drawing an energy line, a bonding, and what are the kinds of orbitals up above? They are called the anti-bonding orbitals. They are higher in energy. They are higher in energy than as if we had a free radical in a p orbital. So that's what that energy line is when we have an even number falls directly in the center. And so now that we have determined that 4, 5, and 6 are empty orbitals, how do I need to add to their label? What should I actually call pi4? Yeah, so it's really, I have a pi4 star, anti-bonding pi5 star, anti-bonding pi6 star, anti-bonding. Okay, so I'm going to go ahead and jump over here. So the 2 carbon is really easy. So I just have 2 molecular orbitals of pi1 and pi2. Pi1 is the only one with electrons. Pi2 is a star. And then I have that, then 1, and then here, and here. And so your drawing should look a lot like that. Okay, I'm going to add other labels because we talked about HOMO and LUMO orbitals and the hexatriene, which is my HOMO orbital pi3, and then which is my LUMO orbital in the hexatriene? Pi4, if we're being really technical, pi4 star. Okay, over in my 2 carbon system, pi1 is the HOMO orbital, and then what is the pi2 star? What's another label we can give it? Yep, LUMO. Okay, so now coming down. 6 plus 2. So I kind of told you that we cannot do Diels-Alder, and I want to make sure that you have in some way proven this to yourself. And so the LUMO orbital, the HOMO orbital of the diene, so that would be the pi3. So I have 6, 1, 2, 3, 4, 5, 6. I can see on the far left, I have plus on the top, minus at the bottom. On the far right, I have plus at the top, minus at the bottom. I'm not going to draw in the middle. You should have that in your drawings. And then what does the LUMO orbital look like? Well, what I know should happen is that the lower lobe of the diene should form constructive orbital overlap with the dienophile. For that to happen on the left-hand side, it would need to be minus overlapping with minus, and so my plus must be at the bottom here. But then I have a node. What should that other side then look like? The top should be a plus, because I have to use the LUMO orbital of the dienophile, and then I go, okay, I have the top lobe of the dienophile. Does it constructively overlap with the bottom lobe of the diene? It is not. And so is 6 plus 2 an allowed reaction? It's not. And so then we say it is the symmetry forbidden reaction. So that's the word that we use. It's symmetry forbidden when it's not an allowed reaction. So then that means if I have room temperature and I take a 6-carbon piece and I throw it in with a 2-carbon piece, I am not going to get a 6 plus 2 reaction. And so then I asked you to draw what you should get. So one thing I want to work with this drawing now, because you're going to be practicing a lot later. So I have drawn this triene in S-trans. Diels-Alder Chemistry, though, occurs in which conformer? Always S6. So I need to do some redrawing. Let's see. So I'm going to rotate around a single bond. I am going to rotate around that single bond right there. So it's going to take this CH3 and flip it to the other side. So then my drawing looks like this. So I flipped that one up, double, single, double, single, double. And then I have a CH2 here. So I'm going to bring these two close to each other. And then this little piece out here is my side group. But I'm going to end up with 4 plus 2 chemistry. But I know all of you at least started this. It might have been right on your page, not so right, but now we can correct it. So I've redrawn in S-trans. It is always the best habit to redraw in S-trans. Okay, let's do one follow-up. So since now I have it in S-trans, this group, is it in the exo position or the endo position? Yes, it is exo. So then to remind you at each of the end carbons, sp2 chemistry, so I have one group that's pointing more interior, that's the endo group, the other group pointing more exterior, so then over here I have those H's. Okay, everyone pretty comfortable with that? Okay, so then we're going to end up doing R4 plus R2. So R4 and R2 we're going to add together. We're going to get a 6-membered ring. It's going to be cyclohexene in character. And so then on the carbon, so here is the carbon that extra group is bonded to. Because I usually have my diene portion be like the 4 carbons on the left-hand side of my cyclohexene. That's how I tend to do it. And so then there is my group. Since it's exo, what is its stereochemistry? So keeping in mind, the endo rule is what guides us. So that electron withdrawing group, the dienophile, comes in from underneath. It interacts with the endo groups. What does it do to the groups? Where does it push them? It pushes them. How? So up or down. That's the only option. What do I do with that endo group? Where do I push it? It pushes it up. So what happens to the exo group? It pushes down. And so then that means for the best drawing, then I need to add dashes to my group right here. It's going to be pushed downward because it is in that exo position. So it needs to get pushed down. Okay, so for your drawing on your page, you may have drawn it like this. Yours might be like slightly tilted to the side, but it would all be the same answer, no matter how you tilted it around in that whole subject. And so that's what our Diels-Alder would look like. Yes, Elliot?
You said you redrew it and made it S-trans. You redrew it and made it.
Oh, yeah, no, you're right. Yes, it was in S-trans. I redrew it in S-cis. Yep, you're totally right.
And then how did you figure out which double bond?
Okay, and so then this is a mechanism question, and so we are going to get at drawing mechanisms. So then let me go ahead and wait on that, because we're going to start drawing mechanisms on our next kind of work of today. So that is definitely a part of the work of today. Alex?
So for these types of molecules where double bond, always going to be
Yes, for conjugation, it always means one away. You might be actually asking a mechanism question again. So I think you're asking, is the new double bond of the product going to be one away from the group?
Yeah.
And it's only a sometimes. Because we've had 70 years of coming up with unique Diels-Alder reactions. And so then, like what Elliot is asking, we're going to get exactly to the mechanism so you know exactly where all those groups are going to be around. Yes, that's it. That's where we're going to be going. That's where we're going to be going. So great leading questions. Like, oh, this is all great, and I'm like clicking them together like Legos, but I want to draw arrows. And we are definitely getting there. Okay, let me go onto your back page. So for the 8 plus 2, so the tetraene. So if I were drawing this full energy diagram for a tetraene, how many individual p orbitals would I have to draw in any line? 8. How many total molecular orbitals would I have to draw? And so then how many total little p's have to draw? 8 times 8 is, that is really tedious to draw an entire energy diagram. So, most of the time, now that you have some experience with drawing some entire energy diagrams, and you will have to draw one for the exam. So you will have to draw one entire diagram for the exam. But most of the time when we're thinking about the chemistry, we do not draw out the whole thing. That's just way too tedious. And so now let's go ahead and talk about this 8 plus 2 reaction and see if we can figure out the answer for 8 plus 2 without drawing the entire energy diagram. And you probably have answers that you can write it in front of you. Okay, so if I have a tetraene, which orbital is the HOMO orbital? Because I would have pi 1, pi 2, pi 5, pi 6, pi 7, pi 8. Which of those is going to be the HOMO orbital? Pi 4. Exactly, because I have 8 electrons, 2 into pi 1, 3 and 4 into pi 2, 5 and 6 into pi 3, 7 and 8 into pi 4, and so then pi 4 is my HOMO orbital. So it is the pi 4 orbital. So then, how do we draw it? So I need my 8, 1, 2, 3, 4, 5, 6, 7, and 8. How many nodes do I have in pi 4? I have 3, so like an n minus 1. So again, like I said, is when I'm just predicting a paper, when I have 3, I do 1 in the middle. I'm like, oh, where am I symmetric? Oh, that looks good to me. Yours may or may not exactly match, but that's okay. We just need 3 in places of symmetry. I always start with plus on the top of my very first. So I would go plus, plus on the top, and then what's going to come next? Yeah, minus, minus. And then what comes next? And then what comes next? Okay. And so then I want to know, is it going to overlap with the LUMO of ethylene? So I know my LUMO is going to be 2 with a node. And so I know that the lower lobe needs to interact with the upper lobe. So negative to negative, so this has to be plus. And then I go across that node, so this now has to be plus. Is everyone following me? I'm doing this pretty fast. And now I do top lobe to bottom lobe. Okay, so what were your thoughts? 8 plus 2, can it happen? Yes, it is a symmetry allowed reaction. It is symmetry allowed. Okay, so that's great. It's an allowed reaction. Okay, so then the last part of this, getting into like the complicated. Just because we say a reaction is forbidden in organic chemistry, does that mean we can't do it? This is the last part of your page. No, it just means we come up with a special trick. I am sure at some point you have had like an adult in your life, a parent, a guardian, a friend say, I forbid you from doing that. But then has that always meant that you didn't do it? Well, no, you just find a different way to do it. It's the same thing with organic chemistry. Just because we have a forbidden reaction doesn't mean that it won't occur. And so then what you should have found with this set of drawings is that you can do a 6 plus 2 if you promote an electron. And so if I have my HOMO star of the triene. Which orbital is this? Which orbital is homostar for a triene? Pi. So triene, I have 6 total carbons. I normally fill in 3 molecular orbitals. I'm promoting an electron up, and so which is homostar? It is pi 4. So 1, 2, 3, 4, 5, 6. How many nodes in pi 4 star? So 1, I'm going to just choose that. So here, negative, negative. Okay, and then I do my 2 carbon piece. Here, going to here. I have overlap. I need to put this here. Oh, look. I have my chemistry. Okay, so I nearly got through all of the answers. You are not turning in this worksheet, but you need to be able to understand all of the principles. And so if you found that me re-talking out all of the principles on this worksheet still didn't make everything make more sense, then we should definitely be meeting in office hours. So I'm not going to collect this and grade it, but you can save this as notes on Diels-Alder, but it's definitely information that you need to know. So you would need to, like, if I gave you another blank for a quiz, which I'm not going to do, but if I were to give you a blank for a quiz, you should be able to fill in all of the blanks with none of my help. So that's the level of understanding you need to make sure that you gain with the Diels-Alder, the symmetry allowed, and then the photochemically induced. So when we add the UV light, that's called photochemical induction. And so then it's our way to help do Diels-Alder with a wide variety of materials. Okay, so now we're going to move into the project for today. So project for today, we are going to start off for this first little bit almost exactly how I've just had you do the worksheet. So we are going to do some of these problems as a group. So I'm bringing the worksheet up on my screen. We're going to do some of these, or I might just bring up a blank page. We're going to do this on the screen, and then I'll have you work with your neighbors to solve some other extra problems. We'll come back together, do a few more things, and I'll send you off to you with your group. Not send you off. Just have you work with your neighbor on the next set of problems. So now we're getting into even more complex Diels-Alder. So we've just looked at one level of complexity. What if it's not 4 plus 2? What if it is something different? I'm sure in all of the rows there's. Oh.
He said he's not going to. That's what he told me.
Okay, does everyone have a handout? Oh, finally.
Oh.
Okay, ready to move forward? So how many times is a person supposed to repeat these and then it helps really remember it? Okay, so I have some repetition within this second worksheet. And so this is again meant so I can talk things out and then you can be drawing. Okay, so for the first set of activities that I want to do now, as we kind of dive a little bit deeper into Diels-Alder, we need to make sure that we totally understand what the diene looks like, what the dienophile looks like. Okay, so the very first question, the chemical reaction is always conducted in a solvent. You're doing that tonight. Our solvents are hexane and ethyl acetate, and this is done usually at room temperature. The diene and the dienophile can freely rotate. It's not locked. And so then I want to make sure we can draw the conformers of one tributed diene. Okay, so what does S-cis look like? So I have a single bond, and then where are those two double bonds? Cis means same, which is the same as like zusammen, right? So same side, and so S-cis looks just like that. Okay, what does the S-trans look like? I have my single bond, and then what is the arrangement of my two other double bonds? Trans to one another, so opposite sides. Entgegen, if we're pulling in like all of our review terminology. The Z and E for our alkene chemistry. So which of those two conformers is lower in energy? This is for the trans. Yep, because the trans big groups far apart. But which is the only conformer that participates in Diels-Alder? This. Exactly. Okay. Yes. Okay, diving deeper. The diene must be electron rich because it needs to be nucleophilic in character. Does that mean dependent group? And so that means like a group attached. That's what pendant means. Does the pendant group need to be an electron donating group or a withdrawing group? If I need my diene to be an electron rich, which should it be? Donating. Yeah. So I need an electron donating group. So what are some examples of electron donating groups? CH3 and methyl, ethyl, isopropyl, short butyl. So all of those would be good electron donating groups. And so any of those alkyl groups, so then if I have an alkyl group, that can be electron donating. But we need to begin to tie in some really good information into our next chapter. And so I want to make sure that you understand that also alcohol groups, electron donating groups. So when I have the oxygen atom, yes, it is electronegative, but it has two lone pairs it can use to donate electron density to something else. The other thing would be amine groups. So amines have one lone pair. So yes, nitrogens are a little bit electronegative, but an amine is also electron donating because it can donate lone pair density in towards something. So those are also good electron donating. Alex?
So I saw this example that already cycling.
We're getting there. Yeah, you're gonna see about every variation upon Diels-Alder by the end of today that you can possibly imagine.
I was thinking of that. It had to be a cis intersection. So
Yep.
The bond.
Uh-huh.
If you had a chair conformer or cycle.
So we don't even so the thing to think about, so you're jumping to like boat and chair. Remember that at room temperature, we can easily convert between boats and chairs. Yep, it's not locked. Okay, so the next one, dienophiles must be good electrophiles. They have to be electron poor. So what is bonded to them? Electron donating or electron withdrawing? Electron withdrawing. Okay, what are some good electron withdrawing groups? Halogens, excellent electron withdrawing groups. Nitro, so we're going to see this more in our next chapter. It should be on our list of good electron withdrawing groups. Definitely. So then the cyano group, the nitrile group would be C triple bond N. And then what I just drew up here, an alkene, is going to be an electron withdrawing group. Yep, so carbonyls. What are all the different kinds of double and triple bond options? So we have carbonyls. In one of the examples you're going to see today, I use an imine, so IMINE, and that's when we have a carbon double bond to a nitrogen. We could also have carbon triple bond to another carbon. So those are good examples of electron withdrawing groups that can be bonded to our dienophile. Okay, so now let's get into the mechanism of how this works. That's what several questions were leading up. What is the mechanism? How does this all work? Okay, so I have here for our next set of questions we're going to deal with for the mechanism, I have just a typical diene, a typical dienophile. So these are just naked. So no donating groups, no withdrawing groups. We're going to build upon this. So how we draw the mechanism, the diene piece is always the nucleophile. Since this diene piece is symmetric, I'm just going to arbitrarily choose to begin the chemistry, begin the mechanism with my arrow at the top pi bond. And how the mechanism works is the pi bond from the diene first attacks one of the carbons of the dienophile. And again, this is completely symmetric, so it does not matter where we begin with the arrow. The Diels-Alder reaction is concerted. It happens all in one step. And so what I ask you to do on the other mechanisms you're going to practice is to number the arrows. And so we would number this as step number 1. Oh, it moved. I don't know why it moved. Oh, move it back up. Okay, so what happens next? When I form a bond, I also have to break a bond, always. So I have to break the pi bond, and the second step is I break this pi bond, and those electrons attack back at the diene, at the other end. And that is arrow number 2. So again, now I've formed a bond. What also has to happen? I have to break a bond. And so then the very last step is I take this pi bond and move it back in there. Okay. So now to arrive at our simple product, here is another thing that I do to make sure I'm drawing everything right. And Alex, this begins to get at your question. So I number all of my carbons that I did the chemistry with. So I began my arrow here. I labeled this is carbon 1, this is carbon 2, this is carbon 3. So I haven't had this issue before with everything moving. Over here is carbon 4. Here is carbon 5. Let's see, 1, 2, yeah, and then here is carbon 6. Yeah, I don't know why it's doing that. Okay, so then for the simple basic product, I have a 6-membered ring. And then I number around the ring. And so then I will go like 1, 2, 3, 4, 5, and 6. So those are the 6 carbons in the chemistry. And then I look at my mechanism. Okay, carbon 1 to carbon 2. So I made a new single bond. Okay, so carbon 1 to 2 is a single bond. Carbon 2 to carbon 3. So that would be right here, carbon 2 to carbon 3. Well, it was a double bond in my starting material, but what is it now? It's single. Okay, so then 3 to 4. What kind of new bond did I form? A new single bond. So 4 to 5. It was a double bond, but what is it now? Single, because where did I move all of that electron? What is the kind of bonding between 5 and 6? It is a double bond. So then I come over here to my structure. There we go. There's my double bond. Okay, let's go ahead. Now we're going to get complicated. What if I don't have a simple dienophile? Because we've had 70 years to practice Diels-Alder, so there's all sorts of options that are created. You're doing a quite complicated Diels-Alder tonight, but one thing I'll go ahead and tie in, because I may forget to say this later, is for your Diels-Alder tonight, you actually have to keep it whole. So with your Diels-Alder tonight, you are using a very strong nucleophile and partnering it with a very strong electrophile for the dienophile. And so then what that means is this chemistry goes very fast. Woohoo! Since we're headed to the spring break, right? So this reaction happens really fast, and it happens so fast, actually, to keep it controlled, we have to keep the reaction cool. I saw that some of you were already logged on to the pre-lab because you have labs tonight. Probably some of you just have it tomorrow, but you'll be reading all about it. It is a very fast reaction because we have a strong nucleophile and a strong electrophile. Okay, so let's look at these dienes. So the dienes, again, keeping in mind, they are our good electrophiles. When they get complicated, we have to very carefully evaluate the nature of the dienophile so that we know exactly how the chemistry occurs. And so here's how I conduct my analysis of dienophiles. What I do is I draw a box around my electron withdrawing group. And that's so I don't get confused about what's my electron withdrawing group, and I don't try to do chemistry with it. Then I know that this carbon right here and this carbon right here are going to be the two involved in the chemistry. So there should be no arrows with the withdrawing group. This is going to make more sense as you start practicing mechanistic withdrawing. I know that the dienophile is my electrophile, but now my dienophile is not symmetric. So we have to figure out which of those two carbons is the most dipole positive. So here's how we do that analysis. So we know that the withdrawing group is pulling away electron density. So it is as if I am pulling electron density away and towards this other side. So if I'm pulling electron density towards the withdrawing group, what dipole character am I going to end up with on this side with the electron withdrawing group? Positive or negative? Negative, exactly. I am pulling electron density over to the withdrawing group. This side becomes dipole negative, and so it is this distant carbon that is dipole positive. What that means, it is the distant carbon that will be attacked in that very first step of Diels-Alder. Okay, let's do a second example. Okay, so this is another really good dienophile. What is my electron withdrawing group? Yeah, so then I'll even be more specific, the aldehyde. So the aldehyde is my electron withdrawing group. So I like to draw a box around my electron withdrawing group. Okay, this is just my electron withdrawing group. It's not involved in the chemistry, the mechanism at all. These are the two carbons involved in my chemistry. If I label the top one as carbon A, the bottom one is carbon B, which one is my dipole positive carbon? Yep, carbon A. That's my dipole positive carbon. It's the one that will be attacked in the first step of Diels-Alder chemistry. Okay, now your turn. So with your neighbor, solve for the next string. Where is your electron withdrawing group? What are the two diene carbons? Which one is the dipole positive carbon of your two? Remember, don't get confused by what your electron withdrawing group.
Why is the top half of the grid part?
It is not participating in the Diels-Alder chemistry see it all. So I like to box it in like all of that. No.
No, I'm serious. No,
Okay, do your answers look like mine? Following. See. Oh, yeah, so it is this. Yeah, because we had it done for a week.
So you wanted to like this first weekend?
This is out of your, out of your. Okay, any questions?
Why does the entire top have a lot?
And so I just more circle the entire half of the top of the cyclopentane because then I'm not confused that any of those carbons participate in the chemistry. And so it is really the nitrile portion that is withdrawing, but then that's my way to focus on, I only care about like these two alkene carbons for the Diels-Alder mechanism.
Okay.
Yeah. It's just kind of a way to double check my work when I go through and draw an entire mechanism. Okay, next up. So we've just looked at complicated and a diverse set of dienophiles. Guess what comes next? A complicated and diverse set of dienes. What can all of the dienes look like? Okay, but first I want to do a practice. So let's do a practice of just a normal diene with a complicated dienophile. And so here is our dienophile, our two carbons of our alkene. Which of these two carbons is the dipole-positive carbon? The one on the top or the one at the bottom? The one at the top, so it's my dipole-positive. Since my diene is not complicated, then what I can do is I'm going to see if I move this more to the middle of my page. So then my first attack always has to be to the dipole-positive carbon. Since my diene is symmetric, then I'm going to go arrow number 1 is there. So I'm always attacking my most nucleophilic carbon. Sorry, my most electrophilic carbon. And then arrow number 2. And then arrow number 3. And then what does the final product look like? So I have my 6 carbon ring. Keeping in mind that I go through in number. And so I'm going to number 1, 2, 3, 4, 5, 6. And 1 to 2 is always my attacking carbon to my most electrophilic carbon. Then what I see is, on carbon number, so that'd be 1, 2, 3. So on carbon number 3 is my aldehyde group. What is the proper stereochemistry? So yes, going towards the back, exactly. We have the endo rule. Our dienophile always comes in from underneath, and so we should make sure that we draw that underneath. There's 4, there's 5. Here's my new double bond, 5 to 6. Yes. No, it doesn't. It doesn't. Clockwise, counterclockwise, you could begin with a different carbon being carbon 1, and so yours is less tilted to mine. It does not matter. Okay, so what does the next one look like? So I'll give you like a minute to go ahead and draw your arrows, number your arrows, and draw the product for this next Diels-Alder reaction. Okay, does yours match mine? Perfect, okay. Yes, Bracken? Oh, you're right. See, I do things wrong in the first session, and then I just repeat it in the second session. You're right. I left those off. And then what I want to highlight, what is the hybridization of these two carbons? It is sp2. And so then what is the geometry at sp2 carbons? It is trigonoplanar, all the atoms in one plane, so we just draw it on the straight line. There is no such thing dashes and wedges on it. Okay. So now, complicated dienes. So let's go ahead and talk about dienes. Now I've given you, so in the first block, we have a diene. What I want to highlight about this diene is I have an electron donating group on carbon 2. So now we have to decide which carbon 1, so is it carbon 1 or is it carbon 4 that has the most electron density? And so here is how we think about that situation. That away. Setting. I've somehow ended up in a different mode. There we go. Okay, here's how carbon 1, carbon 2, carbon 3, and carbon 4. So I'm going to number them that way. Here's how we think about it. An electron donating group, it is as if it's pushing in electron density here to carbon 2. Okay, can carbon 2 have 10 electrons surrounding it? No. So it has to push electron density from its pi bond out towards carbon 1. And so which carbon is most dipole negative? Carbon 1 or carbon 4? Carbon 1. And so that means for our mechanism, an attack will begin at carbon 1 when we have a donating group on carbon 2. So you can either memorize the fact that carbon 1 is most nucleophilic when there's a group on carbon 2, or you can go through what I've just done and kind of think through how the electron flows. Now let's go into the second block. Second block is different. Now I have a donating group on carbon 1. But what annoying way did I draw out the site? I drew it in. Yeah, I drew it in S-trans. How does it always need to be drawn for actually us to do a proper analysis? It has to be in S. And so then how I see it in my mind is I flip around that single bond. And so I am flipping this CH2 over here to the other side. I'm flipping it around. And so then here, double bond up, and I have flipped it that way. So this drawing right here is how I see it in my mind in S6. I'm going to label the carbons again. So this would be carbon 1, carbon 2, carbon 3, and carbon 4. So which carbon is most dipole negative when the donating group is on carbon 1? So here's how we have to think about it. So it is as if I am donating all this electron density towards carbon 1, but can carbon 1 handle 10 electrons around it? It can't. So where does it have to push electron density towards? It has to push electron density over here. Can now carbon 3 handle 10 electrons? It can't. So then I have to push electron density out over here to carbon 4. So carbon 4 is the most dipole negative carbon. This seems odd. So when the electron donating group is on carbon 1, which carbon is actually the most dipole negative? Carbon 4. And it seems odd, but time and time again, in 70 years of Diels-Alder, this has proven to be true. So it is the 4 carbon, the carbon on the opposite side, that actually becomes the more dipole negative carbon and the most nucleophilic. Yeah, Elliot?
Carbon 4. It wouldn't it start on the left and go?
Oh, you're just numbering back. You're just numbering different than I am. I'm saying that the group is on carbon 1. I'm arbitrarily numbering here. I'm not doing IUPAC numbering. I am just doing numbering for a chemical analysis. Okay, so now your turn. So with structures, diene structures 3 and 4, which carbon of the diene is the most nucleophilic? And so it could be helpful again to put a box around the electron donating group. Yep, OH. I had it on our list of electron donating groups. Alex?
So when the group is on the second carbon, why does it set the third carbon?
That's the only way the electron flow works.
No, that's anyway. So when they come first carbon, but then why is it that it's so late for water?
Because I don't have the orbital, I don't push it that way. That would be as if I am breaking a single bond, moving electrons out. So I am moving electrons through the p orbital. And then again, what I'll just highlight is that how do we know this is true? From 70 years of doing Diels-Alder. We know that this is how the electron flows. Okay, same answers that I had on the dipole negative carbon. Okay, so now let's do practice of a complicated diene adding to complicated dienophile. So that's what is here on this next block. Okay, so my starting material, my diene. And so now I'm going to number it carbon 1, carbon 2, carbon 3, and carbon 4. Which carbon on this diene is the dipole negative carbon? Yep, carbon 4. So I'm going to label it as dipole negative. So then I'm going to come over here. I have this 2 carbon system. And so with this 2-carbon system, so this is my withdrawing group, is it going to be carbon A or carbon B that is the most dipole positive? A. So then, how do I draw my arrows? So the first attack must always be most negative to most positive. So what is arrow 1? So negative to positive. That's arrow 1. And then, where's arrow 2? So then it's going to be then the B carbon to the 1 carbon. That's arrow 2. And then here's the 3rd arrow moving in. Oh, that's fine. Wherever. Yeah, wherever. You can see I just drew it on that as well. So what can be, so notice, like, what annoying thing did I do here? They're like arranged flip-flop to each other. So sometimes what can be easier, and this is just going to totally be your own personal decision, sometimes it can be easier to redraw the starting material so that they just directly click together, rather than having arrows like crisscross over the top of each other. So then what does the product look like? So I have my 6-membered ring. I'm going to go 1, 2, 3, 4, 5, 6. Okay, so how do I label? So that CH2 needs to be 5, that needs to be 6. So on 1, I have a CH3. And then to 2 single, 2 to 3, I have a double bond. So notice as I'm going around, I'm like following my label. So there's 4, 4 goes to 5, 5 go to 6. Okay, so 6 is where I have that aldehyde group. And so what's most important about your drawing, and this is to get Brecken's question, what's most important about your drawing is notice that the CH3 and the aldehyde are on neighboring carbons. And then notice that the double bond of the cyclohexene is like 1 removed from the CH3. That would be the proper orientation. Alex? And so now that's the next step. So withdrawing groups, where are they always? Following the Indo rule, they are always back because they're underneath. So I should go in and fill them in with dashes. That's usually my very last step of my proper drawing. And then the CH3 in my starting position was the CH3 in the Indo position or the exo position. Exo, so where does it get pushed? Remembering that Indo gets pushed up as the dienophile comes in under Indo. Indo gets pushed up, so exo gets pushed down. So the fact that it's pointing up. And so then, Cami, let me just do a quick redrawing for you. So keep in mind when we draw in S-cis, at the end carbons, there are 2 bonds. One is up, one is down, one is up, one is down. And so these inside ones are labeled as the Indo bonding position. These outside ones are labeled as the exo bonding position. So the Indos get pushed up, the exos get pushed down when we bring in the dienophile. Okay, so what is your objective? We are going to reconvene out of 25 after. So now you can take break. And then at 25 after, I'm wanting you to be through most, if not all, of these other practice reactions. So now I'm sending you to your group to do the next set of practice reactions. So you need to make sure that you identify the most dipole-negative carbon of the diene. the most dipole-positive carbon of the dienophile. Properly draw your mechanism. And since we've already studied stereochemistry, add stereochemistry into the drawing of your final product. Okay, go. So I'll let you decide in your groups, like when you're going to take a break, but we're going to reconvene at the 25.
Yeah.
Yeah.
All right. They both are.
So far, man, I don't get it. Yeah. Maybe another bisector board.
Yeah.
Shouldn't there be a double bond between two?
Yes.
Okay. You have your drawing.
No. You're right.
Not even.
Okay, now that everyone's back, it looks like several of the groups have prepared answers. I have a couple of my answers up here. And so now we've gone through all of the information that you need to finish the rest of this worksheet. So the rest of this worksheet is take home for you. So the rest of this worksheet is homework. But so that you understand what I have going through the next steps. So here we've been drawing reactions, mechanisms, the products. We have been adding stereochemistry because I've actually had us practice that all the way throughout. So in the next part, I have you like really thinking about stereochemistry again. And if you're not sure you understand my stereochemistry, I have it all written out again. And then even more practice problems on drawing the reaction mechanism and drawing the product. So you have lots of different practice problems. At the very end of this worksheet is another just kind of making sure you do understand the molecular orbital theory. And so that will complete out our Diels-Alder chemistry. So one thing I really want to encourage you to do, because we've been talking a lot about this in regards to like exam preparation, is again to think about if I were to give you all of these questions blank with no help, could you now solve for them on your own with no neighbor and without me talking them out? That's where you want to make sure you're at by the end of break. Because when we come back from break, we're starting new chemistry. So you want to make sure that you have this all solidly in your mind. Okay, so if you'll go ahead and put those worksheets away, now we're going to start into the next chemistry of chapter 15. Yes, on a Monday from spring break. Not this coming Monday, but the Monday of spring break. So I'll take this at the beginning of class. Okay, next, the not unique reaction of conjugated alkenes. We've just studied the one unique reaction that conjugated alkenes can participate in, and now we're going to go back and do a little bit review of what are just the typical alkene reactions. And how do they happen when I have conjugation? Open. Okay, does everyone have worksheets? Anyone missing? Oh. I think that covers Brecken. Everyone else have a worksheet? Okay, back to alkene chemistry. So reaching way back to chapter 7, either 7 or 8. 9 was alkynes, so it'd be 7 and 8, how to make an alkene and then reactions of alkenes. So that would have been chapter 7 and 8. So reaching back to 7 and 8, we learned about some very typical alkene reactions, and we're going to look at a few of them again, and then how these alkene reactions proceed when we have conjugated alkenes. But to review, let's just start. What if we have a normal alkene with Br2? How did that reaction proceed? So to remind you, it was very SN2-like. When I have an alkene and I am adding it to some reagent, what always behaves as the nucleophile? The nucleophile is always the double bond, the pi bond. So the pi bond is the nucleophile. So we call these electrophilic reactions because we're adding an electrophile to the pi bond. So the first step, the pi bond attacks at one of the bromines. And then what else happens? Yeah, we definitely have to break a bond, but what else did we draw? We drew in one other arrow. Yeah, the bromine attacking back. Okay, and so then we kind of don't draw that anymore now that we're no longer like just beginning organic chemists, now that we're leaping organic chemists. We really don't always draw back that back attack of the bromine. I'll go ahead and add it to my notes just to be consistent with what we learned about in our earlier chapter so we can attack back. And then what does that intermediate look like? Yep, so I have a cyclic bromonium ion intermediate, and then I kicked off and then I still have that bromide out there. I had kicked it off as a leaving group, and it's still floating around. And then what? Is a three-membered ring stable? Lots of strain, right? Lots of strain, and I have that positive charge on it as well. So there's lots of strain within that three-membered ring. It is not stable. And so the bromine, that bromide, is going to attack as a nucleophile. So a couple things to remind ourselves about is that bromide going to come in on the same side of the cycle or on the opposite side? Opposite side. And so then that's why we labeled this kind of chemistry as anti-addition. It's going to come in opposite. Is this bromide going to attack at the most substituted carbon or the least? And wait, so before you answer, how strong of a nucleophile is a bromide? So bromine, large, means it's polarizable, but it's electronegative, so it's kind of stable with charge. So how nucleophilic is that bromide? So like very strong, moderate, weak. Yeah, I'd go like moderate to weak. So now thinking through that and keeping in mind everything that we studied with epoxide chemistry, if I have a moderate to weak nucleophile, does it attack at the most substituted carbon or the least substituted carbon? Most substituted, because the most substituted carbon is the most dipole-positive carbon. And so our bromide is going to attack at the most substituted carbon, and then I break that bond. Alex?
What are the carbons that are on it that are electrons?
Okay, so then, great question, and then we went through this with the epoxide chemistry. I have these two electron donating groups. They are able to donate electron density that can then be pulled away from the bromine. So the bromine is going to pull from the left because that is where I have the most electron density. Yep. And that's how we think through that principle. And so then drawing our final product, one bromine is directly down, the other bromine we can draw up. What's even better is to add dashes and wedges. And so if I draw one of the bromines on a wedge, how should the other one be drawn? On a dash. If I have chirality, that would be the best way to draw it. Okay, so then that was bromination. So our chemistry is likely practiced when we were testing our cyclohexene material. Okay, next, what if I have hydrochloric acid? What is always the nucleophile? Pi bond, the double bond, and of H and Cl, the pi bond is going to attack which? The H, the proton, because it is dipole positive. I form a bond. What has to always happen next? I break a bond. So I break the H to Cl bond, put those electrons onto the Cl. Oh, I have a carbocation intermediate. Okay, so carbon on the left, carbon on the right. Which is going to be better as the carbocation? The left. Yeah. No, it doesn't matter which bromine.
I think the stereochemistry. It can't be stereochemistry.
Oh, right. I said if it were a chiral center. Yes, I see. Yeah, if it were a chiral center, then we're very careful, one on a dash, one on a wedge. But you are totally right that in this very particular example, I have two of the same group, so it's really not chiral. Yeah, I see what you're saying. Okay, so again, coming back here, our carbocation has to be on the carbon on the left because we need the carbocation where I have the most electron donation. And so then it's the carbon on the right that gains the new hydrogen. So it gained the new hydrogen, of course, before it already had one, because I had one here. So it gained the new hydrogen. And then what is going to happen in the next step? Yep, so the Cl is going to attack. And then I draw my final product. Okay, so now getting a what if this carbon were a chiral center, what would be the best way to draw the bond to the chlorine? Dash, wedge, something in the middle, the squiggly, right? Because a carbocation is trigonoplanar, it's flat, so the chlorine can come in underneath, or the chlorine can come on the top, so we draw it with the squiggly. So Sarah, I bet this is brand new to you, drawing on a squiggly, yes. It's a very American thing. It's kind of a new American communication method on representing that if the compound were chiral, we would have a racemic mixture, and half of the molecules, the chlorine would be on a wedge, the other half, the chlorine would be on a dash. And so how we decided to communicate that now is with the little squiggly. Okay, questions there? Now, what if? What if we have conjugation? So we have a little bit of a study that we need to do first. Okay, so here's my fact about conjugation. In a conjugated system, or my question, in a conjugated system, are the pi bonds at the end or the middle most likely to participate in alkene chemistry? How do we know? We did kind of answer this before, but in case you're not sure you remember, let's go ahead and go through this process. So to solve, we draw the energy diagram for the bonding molecular orbitals of hexatriene, and then we're going to answer the questions below. Okay, so for hexatriene, how many carbons are in this system? 6. So I have 6 carbons. So how many p orbitals do I need to draw in my energy diagram? Yep, I need to draw 6. How many bonding molecular orbitals will there be? 3. So I need to draw pi 1 and pi 2 and pi 3. You all are getting perfect at drawing your p orbitals, right? Oh, 18. I'm going to go ahead. I have electron 1, 2, electron 3, 4, electron 5, 6. Those are my bonding orbitals. So what kind of orbital overlap is in pi 1? All? Yep. What's different about pi 2? So plus, 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 then minus, minus, minus. What's different about pi 3? So it'll be plus, plus, minus, minus, plus, plus. I hear some of you mumbling along. Okay, there we go. So now we need to look at the kinds of bonding between each of the carbons. So we have carbon 1, carbon 2, 3, 4, 5, and 6. And so do our pictures represent that we have a full double bond, partial double bond, or no double bond? Okay, carbon 1 to 2. Look through all of the 3 pictures of the bonding between carbon 1 and carbon 2. So there's our 3 pictures. What kind of bonding do they show between carbon 1 and carbon 2? Full, partial, none. Full. Yeah, all 3 pictures show good orbital overlap, good constructive orbital overlap. So we would rate that as a full double bond. It has full double bond character. Okay, carbon 2 to carbon 3. What does it look like? Yeah, I do have a node in pi 3, don't I, between carbon 2 and carbon 3? And so how would you rank that? Full, partial, or no double bond? One of the picture has a node, so Aurora, exactly right, partial. Yeah, so I have partial double bond. Okay, carbon 3 to carbon 4, thoughts? Yep, because in one of the pictures, I have destructive orbital overlap with a node, so it's partial. Carbon 4 to carbon 5. Carbon 5 to carbon 6. Full. Okay, so thoughts? Which pi bonds are going to be the most reactive for alkene chemistry in a conjugated system? The end bonds or the middle bonds? Yep, the ends. The ends, because they have full double bond character, they are the most nucleophilic. I have the most localization of electrons at the end, and through the middle, I have all of this various sharing going on. So let's go ahead and draw what chemistry would look like. So in conjugated systems, the most likely to participate in alkene chemistry are the end carbons. The chemistry will happen at these pi bonds because they are full pi bonds, more nucleophilic than the partial pi bonds throughout the center, or something like that, is how I explain it. Okay, so let's do chemistry. So this is your next page. So I asked you to do 1,3-butadiene with HCl. So 1, 2, 3, 4. There's my butadiene with HCl. And we're going to do what is a typical reaction, which is known as a 1,2 reaction. Our diene totally symmetric, so I'm just going to take the pi bond on this end, attack at the proton, break the hydrogen to chlorine bond. Which carbon is going to become the carbocation, the one at the end or the one at the middle? Yep, the middle one. And that carbon at the end gains the new hydrogen. Since I'm in line angle, I'm not going to draw in that new hydrogen. And then what happens at the next step? So the chloride, it will attack. I do have a chiral center here, so we can draw the squiggly with the chlorine. So that was my product. It's called the 1,2 product because at carbon 1, I added the new hydrogen, and at carbon 2, I added the new chlorine. So it's called a 1,2 product. But is this the only way the chemistry might proceed? The answer is no, and we as organic chemists love to look at all of the options, explore all of the options. So let's go ahead and go to the next problem. And so then we're going to work on drawing the 1,4 product of 1,3-butadiene with HCl. Alex?
So both the ones on
So it's symmetric. So no, actually I did skip over that. If you go back and thoroughly read all my notes, we only ever use just one equivalent of an electrophilic reagent. Okay, so now I'm going to add chemistry. And so for the 1,4 product, what happens is we do SN1 to get the carbocation, but then we have resonance, and then the chloride adds. So let's go ahead and go through those steps. So the pi bond attacks with the proton. I break the HCl bond. And then again, I get the carbocation at the middle carbon. So a quick review, how do we draw resonance? So we always move electrons from high density to low density. So we use our pi electrons, we move them to the next bond. What is that going to look like? So now my double bond is here in the middle. I still have carbocation character. Where is it? Yep, it's on the left carbon. Okay, and then now my chloride comes in and adds. And this is called the 1,4 product because we added our new hydrogen at carbon 1 and then our new chlorine at carbon 4. Okay, and that pretty much fills the time for today. I'll answer Elliot's question, and then I'll kind of explain the rest of this topic for you. Elliot?
How often is that listening?
Oh, that's what you're going to answer for yourself. That's like my cliffhanger. Like, oh, and so then that'll make sure that you want to really finish this packet, because that's the cliffhanger that's in this packet. is comparing the 1, 2, and the 1, 4. So to finish out these pages, I have practiced the 1, 4 with BR2. Again, drawing the BR2 mechanism as if it goes through a carbocation intermediate. So that's the next thing I have you practice. And then I learned about information directly related to Elliott's question, which is how often do we see 1 to 2? How often do we see 1 to 4? And so then that takes you through the next couple of pages. And then at the very end, I have just a little bit of a reminder of allylic chemistry, and this finishes off chapter 15. So all of this is very straightforward. We've seen this chemistry before. So the rest of this packet is review of alkene chemistry we have seen before. Oh, and so actually, oh, yes. So on some of yours, it does look like you have an extra left page. It says Introduction to Diels-Alder Chemistry, 11 forbidden reactions. Do all of you have that? Okay, so I must have accidentally grabbed an extra page to put on my photocopier, so we've already done that. This could be the blank that you use to quiz yourself and see if you're good at doing that chemistry. But yeah, so then you don't need to do anything with the last page. Okay, so then all of this should be done Monday when you come back from spring break. You could have like a couple that you leave blank because you're just really not sure of it. But my plan is to only spend about the first 15 minutes of class reviewing any final questions. I'll take it and then we move on to our next chapter. Okay, have a great break.